Hello, my name is Lasse Rahbek and I will be presenting the paper Parametric Grid Mapping Design Tool for Freeform Surfaces using a Genetic Algorithm. The presentation is divided into 4 parts: Introduction, Methodology, Results and Analysis, where I'll present some of the most interesting cases, and lastly a conclusion. The main research goal is defined as to develop a parametric grid mapping tool for freeform surfaces. The idea is that there is a great potential in using other grid patterns than the classical repeating patterns most often used today. It is a development and improvement of a concept first proposed by James Richardson. This paper introduces multiple objective optimization, horizontal forces, and a novel grid repair algorithm called Rule Based Kinematic Stability Repair, and also a methodology that is not limited to freeforms with a rectangular plane. The methodology section briefly explains the mechanisms of the design tool, most importantly the parameterization, i.e. how the grid is allowed to adapt to the forces affecting it. So basically, every node can move in 2 dimensions in a confined space, and every grid member can be turned on or off. The 2-dimensional grid is then projected to the base surface. The load area can be calculated with Voronoi diagrams because the grid shell is usually dominated by live forces. If you go into detail, then the whole process can be illustrated using 2 nested loops with 5 stages. The first stage is the rule-based kinematic stability repair algorithm. This algorithm takes any grid configuration and it adds or removes grid members using defined rules to create a kinematic stable solution. This is opposed to the ground structure approach that only adds elements until every node has minimum 3 active connections. The repaired grid is then verified with 4 control procedures. Any non-valid solutions are discarded and replaced by a new stable grid configuration. In stage 2, the repaired grid is projected on to the base surface that is created with dynamic relaxation. And this is then used as input to a finite element analysis using Karamba 3D. Lastly, the solution is evaluated to measure the fitness of the solution. There are 3 possible fitness objectives: minimization of mass, minimization of strain energy, which is basically the maximization of stiffness, and minimization of the average length deviation, which is an aesthetic objective that encourages the algorithm to use grid members with almost the same length. The optimization is constrained to only produce grids with a positive eigenvalue that every active node is connected, and to abide by the rules defined in Eurocode 3. The genetic algorithm initiates when every solution in a generation has been evaluated. The genetic algorithm uses the principles of evolution to find optimized solutions. The output of the genetic algorithm is the Pareto front. It is a set of dominating solutions where it is possible to control the weighting between the defined objectives. The weighting used in the following cases will be roughly equal. The Scottish mathematician and biologist Darcy stated that the form of an object is a diagram of forces. This is very much also the case for this result. We can see that the algorithm adapted to the affecting forces by creating these braced legs to transfer the vertical forces to the ground. This pattern is so effective that only 2.4% of the strain energy originates from bending forces. Gridshells can be very sensitive to horizontal forces, and even a small disturbance can lead to failure. So in this example, the grid is affected by a horizontal force and vertical force simultaneously. The algorithm reacted to this by adding more elements to help disperse the horizontal force. And the structure can still be defined as mainly funicular. This is also evident when looking at the figure illustrating the axial forces. You can see that almost the entire structure is in compression, illustrated by the color red. This case examined if the algorithm could add a third aesthetic objective and still produce optimized solutions. In this case, the minimization of average length deviation was added to minimization of mass and strain energy. You can see from the illustrations that the length of the different grid members doesn't deviate very much. This gives the grid shell a more uniform appearance. And the data shows that the third objective only have a limited impact on the structural performance. The grid shell still exhibits membrane behavior. This case was examined to see how the algorithm would perform on a more complex base shape. The algorithm created these braced legs to transfer the forces to the ground, but one can also notice some vague arch configurations within the grid topology. The bending energy in the grid contributes with roughly 37% of the total strain energy, though some of this could originate from the unorthodox shape. The solution still exhibits good membrane behavior. So, to summarize, this project shows that there is a potential in using adaptive grid patterns rather than the classical repeating grid shell patterns. The algorithm in this program produces optimized solutions with up to 3 different and conflicting objectives. It can handle horizontal forces, and the Rule Based Kinematic Stability Repair algorithm aids the optimization procedure. And finally, it can be concluded that the concept introduced by James Richardson has been successfully implemented and improved to yield better results. Thank you for your time.